Hello and welcome back to another deep dive. Today, we're going to transport you straight into the chemistry laboratory.
Oh, I like the sound of that.
I want you to picture a very specific scene.
Yeah.
Imagine you're standing at your workstation, you're wearing your white lab coat, you are holding a test tube.
Okay.
Inside, there's a pale yellow liquid called aniline. You've mixed it with acid, and the whole test tube is sitting inside a beaker full of crushed ice. It looks completely calm, it's clear.
Looks harmless.
Exactly.
Yeah.
But if you take that test tube out of the ice and just place it on the bench to warm up, suddenly, whoosh, bubbles start rushing out. It starts decomposing furiously, almost like a soft drink that has been shaken up.
That is a very dramatic but a very accurate description of what happens in the practical lab. And do you know why that happens?
I have a feeling you're about to tell me.
Because you have essentially created a chemical time bomb.
A chemical time bomb. That sounds dangerous, but also quite exciting for a chemistry student. So what exactly is this volatile thing we're building today?
Today, we're doing a deep dive into the method of preparation of diazonium salts. This is one of the most critical topics from Unit 9, amines in your Class 12 syllabus.
Right.
And to answer your question, that time bomb in the test tube is the benzene diazonium chloride.
Diazonium salts. I remember seeing the structure in the insert textbook. Usually looks like a benzene ring with two nitrogen atoms sticking out of the top.
That's the one.
But here's my question. Why do we care so much about making something that falls apart if it gets even a little bit warm? If it's a time bomb, why are we building it?
That is the right question to ask. See, we don't prepare the salt to keep it in a bottle on a shelf. You will never find a bottle of diazonium salt in the storeroom.
Okay, so it's not for storage.
We prepare to use it immediately.
Mhm.
Think of the diazonium salt as the most important detour in organic chemistry. Without this detour, we simply cannot make many of the dyes that color your clothes or many of the medicines you might find in a pharmacy.
So it's a stepping stone, a very unstable, very reactive stepping stone.
Precisely. It's a means to an end.
Okay, so it's like a layover on a flight. You don't want to live in the airport, but you have to stop there to get to your final destination.
That's a great way to put it. And in this deep dive, we are going to master exactly how to construct this layover. We are going to break down the reaction known as diazotization.
Let's get into the core idea then. For the student listening who might be struggling with the organic chemistry jargon, or maybe they find amines a bit difficult, what is the simplest way to understand what's happening here?
At the simplest level, think of it like this. You start with an aromatic amine, usually aniline. Now, aniline has a passenger attached to its benzene ring, the amino group, which is nitrogen with two hydrogens. That's next to NH2.
Right, the NH2 group, the amino group, that's our starting passenger?
Correct. Now, we use a reagent called nitrous acid, or HNO2, to swap that stable passenger for a new, very unstable passenger.
And that new passenger is?
The diazo group, which is named as N2 plus A.
So we are trading a comfortable passenger for a crazy unstable one.
Exactly. Imagine the aniline molecule. The nitrogen is holding on to two nice, calm hydrogens. Then nitrous acid comes in and effectively replaces those hydrogens with another nitrogen atom.
So now you have two nitrogens stuck together.
Yes, sticking out of the ring, you have two nitrogens stuck together. They're holding a positive charge. They are, repelling each other, and they are just ready to leave.
I like that mental image. Two nitrogens stuck together, vibrating, wanting to break free.
Yeah.
That explains the bubbles we talked about earlier, right?
Yes. If they break free, they leave as nitrogen gas, N2. That is the bubbling. But before they bubble away, while we keep them cold in the ice bath, that cluster is called the diazonium salt.
Okay, let's look under the hood. What is really happening at the particle level? How do we actually make this happen in the lab?
So mechanically, you need three things: aniline, sodium nitrate, that's NaNO2, and hydrochloric acid, HCl.
Wait, you mentioned nitrous acid HNO2 earlier, but now you're saying sodium nitrite and HCl. Why the difference?
Ah, good catch. This is a critical point for the board exam. You cannot buy a bottle of nitrous acid. It's too unstable. It degrades very fast.
So you have to make it.
You have to make it right there inside the beaker. We call this preparing it in situ.
In situ, that means in the situation or on site.
Yes. You mix the sodium nitrate with the hydrochloric acid. They react instantly to form the nitrous acid, and in the acidic solution, this forms a very reactive particle called the nitrosonium ion, or NO+.
Okay, nitrosonium ion. That sounds quite intense.
It is the main actor here. The aniline attacks this ion. There is some shifting of protons, some rearrangement, and eventually you end up with benzene diazonium chloride.
So if we had to give an exam-safe definition for this whole process, what would it be? If the question asked, define diazotization, what should the student write?
You should write this down. Diazonium salts are prepared by diazotization, the treatment of aromatic primary amines with nitrous acid in acidic solution, forming thermally unstable salts.
Thermally unstable. That is the academic way of saying keep it on ice or it explodes.
Right. Basically, yes. And there is a huge misunderstanding trigger here that I want to flag immediately.
Please do. We want to avoid losing marks on silly mistakes.
Students often think any amine can do this. They see an amine group and think, great, I'll make a diazonium salt.
But you can't.
You cannot. This reaction works for aromatic primary amines, like aniline, where the nitrogen is attached directly to a benzene ring.
What happens if I try it with a straight chain amine, like just a regular carbon chain?
You mean aliphatic amines? They are catastrophic for this purpose. They form a diazonium salt that is so unstable it decomposes instantly, even at cold temperatures.
So you just get a mess.
You get alcohols, bubbles, a mess. It does not stay as a salt, so remember, it must be aromatic.
Got it. Aromatic only. Now, I want to help our listener really visualize this process. You mentioned this like a detour, but I've heard you use a different analogy before, something about surgery.
Yes, the molecular replacement surgery analogy. This is my favorite way to explain why we go through all this trouble.
Walk us through it.
Think of the aniline molecule as a patient. The amino group, the NH2, is the body part we need to operate on. Now, usually that amino group is stuck on very tight. It's hard to just swap it out for something else directly.
Okay, so the patient needs a transplant, but the original part doesn't want to leave.
Correct. So nitrous acid acts as the surgeon. The process of diazotization is the surgery. We turn that safe amino group into a diazonium group, Magus N2 plus O. Now think of the diazonium group as an open incision.
An open incision, that sounds painful.
It represents vulnerability. It's an open wound. You don't send a patient home with an open incision, right? It's unstable.
No, you finish the surgery.
You have to finish the surgery immediately. That is why the salt is unstable. We create this open wound state specifically so we can easily attach a new group like chlorine or bromine or cyanide in the next step.
That makes so much sense. So the diazonium salt isn't the final product. It's the patient on the operating table, cut open and ready for the new part to be put in.
Exactly. And to answer why this concept exists, it exists because the amino group is usually too friendly. In chemical terms, we say it's activating.
Meaning it reacts too much.
It makes the ring react too much or in the wrong places. By turning it into a diazonium salt, we create a reactive intermediate that lets us swap that nitrogen for almost anything else later. It solves the problem of how to replace an amino group.
I love that. It is solving a specific problem. Now, I want to try a visualization exercise. If you are listening and safe to do so, close your eyes for a second. Let's play a mental movie.
Okay, picture an aromatic ring, a flat hexagon. Sitting on top of it is a blue sphere. That is your amino group. It's stable. It's happy.
Okay, I see the blue sphere on the hexagon.
Now a yellow wave washes over it. That is the nitrous acid mixture. As the wave hits, that blue sphere transforms.
Into what?
It turns into a bright red sphere. But this red sphere is not sitting still. It is vibrating. Vibrating.
Yes. It is shaking violently. It is holding a positive charge, the N2 plus micronanosicko. It looks like it is about to pop off the ring. That is your diazonium group. It's thermally unstable.
It's shivering because it needs to be kept cold.
Exactly. If you add heat, that red sphere explodes off the ring.
That is a vivid image, the shivering red sphere. That really helps explain the temperature requirement.
Speaking of temperature, let's go back to the lab for a moment.
Yeah.
We mentioned ice cold. How cold are we talking?
Is it just freezing, like 0 degrees?
Strictly 0 degrees to C to 5 degrees C, or in Kelvin, that is 273 to 278 Kelvin.
That is a very narrow window.
It is. In the practical exam or the board theory paper, if you just write cold, you might lose marks. You need to specify 0 to 5 degrees Celsius.
And if I am lazy and I let it get to, say, 10 degrees?
You will see the phenomenon we started with. Bubbles, nitrogen gas, N2, escaping. Your preparation has failed because the salt decomposed.
So the open incision it failed.
It healed poorly, if we use our analogy, and you are usually left with phenol instead of the salt. Now, we keep saying this is important for industry. Can you give me a real-world example? Where does this actually show up in technology?
The biggest application is the dye industry. We use diazonium salts to create azo dyes.
Azo dyes. Those are the bright colors, right?
Yes. Remember our vibrating red sphere? The Diazoniu.
Yep, the one that's about to explode.
In the dye industry, we take that vibrating sphere and we let it grab onto another aromatic ring, something like naphthol. When it grabs that other ring, it stops vibrating. It becomes a bridge between the two rings.
And that structure.
That's the color.
That structured two rings connected by two nitrogens is incredibly colorful. It becomes bright orange or red.
So the time bomb goes off, but instead of an explosion, it grabs a partner and turns into a bright color.
Beautifully put. That is how we get the bright orange in your t-shirt or the ink in your highlighter. It is all thanks to the diazonium salt. That's fascinating. Now, I want to circle back to something you hinted at earlier, the naive assumption. I feel like a student might look at this and say, okay, aniline works, so methylamine should work too, right? It has an NH2 group.
It is the most common trap. You might think nitrogen is nitrogen, but actually, aliphatic amines, those straight chains like methylamines, CH3NH2, behave totally differently.
Why? What is the difference? Why does the ring matter so much?
It comes down to stability. In aniline, the benzene ring helps to spread out or delocalize some of that electrical charge. It holds onto the unstable diazonium group just tightly enough to keep it together at 0 degrees.
So the ring acts like a stabilizer, like a shock absorber for the charge.
Exactly. But in methylamine, there is no ring. There is no stabilization. So if you try to diazotize methylamine, the moment the diazonium forms, it falls apart.
Instantly.
It decomposes instantly to form alcohol and nitrogen gas bubbles. You can never isolate the salt.
So no ring, no salt.
Precisely. The aromatic ring is the anchor holding the unstable group in place.
Okay, we've covered the concept, the visualization, and the traps. Now, we need to make sure our listener gets full marks on the board exam. Let's do a clarity check. What are the specific lines they need to memorize?
Let's break down the exam-safe clarity lines. I will say them slowly. These are the points your invigilator will look for.
Go for it. Number 1.
Number 1, only aromatic primary amines form stable diazonium salts.
And why is that important?
Because aliphatic ones decompose instantly. If the question asks for preparation of diazonium from ethylamine, remember, it is a trick question.
Got it. Number 2.
Number 2, temperature must be 0.5 degrees C.
Because
heat causes decomposition into nitrogen gas. You must mention the temperature range explicitly.
Number 3.
Number 3, nitrous acid, HNO2, is prepared in situ.
That means we mix it in the beaker, right?
Yes. You write the reaction as reacting aniline with NaNO2 plus HCl. Do not just write aniline plus nitrous acid as the starting reagents. You must explain how the acid is made.
Okay. Number 4.
Number 4 is the definition term. The reaction is called diazotization. It is a specific keyword you must use.
And finally,
The last one.
the general formula. The general formula is Rn2 plus X.
And what is the X?
X is the anion, usually chloride, Cl, coming from the hydrochloric acid we used. So benzene diazonium chloride.
Rn2 plus Cl. Okay, I think I have got that.
If you stick to those 5 points, you are safe for any question on preparation.
Fantastic. We have unpacked a lot today. We went from fizzy test tubes to molecular surgery. Let's bring it all together in a short summary for revision before the exams.
Let's recap. Today's core idea was diazotization. This is the process of turning aniline and aromatic primary amine into benzene diazonium chloride.
And we do this using nitrous acid, which we make right there in the pot using sodium nitrite and HCl.
Correct. The mental image you should hold is the molecular surgery. We are creating an incision, the unstable NaCN2+ group.
And like any open surgery, it's delicate. We have to keep it ice cold, strictly between 0 and 5 degrees Celsius. If it gets warm, the red sphere vibrates too much, flies off as nitrogen gas, and the experiment fails.
And the big takeaway, why do we do this? Because it lets us take that stable aromatic ring and get it ready for big reactions like making dyes or medicines that we couldn't do otherwise.
Exactly. It activates the molecule for the next step.
So listener, next time you see that structure, the benzene ring with the N2+, don't just see a drawing. Picture that vibrating red sphere, shivering in the ice bath, waiting for its partner to turn into a bright orange dye.
And remember, you are the surgeon. Keep your patient cold or you will lose them.
That is it for our deep dive into diazonium preparation. You now know how to build the chemical time bomb. Just remember to keep it on ice. Thanks for listening.
Keep learning.